So let's look at this optimization problem here. We have 6 allotments, so this is areas for growing food and veg. Now if we were to say that one allotment has a length of x and a height of y, and we were to say that we're going to fix the total area of the allotment, so the area is 108 meters squared. So this is a fixed value, but what we can do is we can change the length of x. So of course when we change the length of x, the length of y is going to change, but it has to change in such a way that the area remains fixed. And we're going to ask the question, what value of x will ensure that we minimize the amount of fencing that goes round about this allotment? So first of all, we've got to find the length of fencing here as a function of this value of x. So let's look and see what information we have. So first of all, we've got the total area of this allotment. So the area is going to be the total length times the total breadth. So the total length is going to be 3x. So we're going to have 3x and we're going to have 2y. So 3x times 2y is going to equal 108. So we could call that, if you like, equation number 1. Now we've also got the total perimeter of fencing that's required in order to create the allotment. So that's going to be, well, there's going to be 1, 2, 3x here, there's going to be another 3x and another 3x. It's going to be 9x plus, now there's going to be 1, 2, 3, 4, 5, 6, 7, 8y. So 9x plus 8y is equal to, we'll just call it L, because L is going to be the total length of fencing required. We can call that equation number 2. Now we said that we're interested in finding the length as a function of x, so I can put it down here. We're looking for L as a function of x. Now what we have up here at the moment, we've got L here, but L is a function of x and it's a function of y. We don't want it a function of y, we want to get rid of this. So we could say L is equal to the value of 9x plus 8 times the value of y. But we can find y from this equation here. So the y is going to be equal to 108 upon 2 times 3, which is 6x. So it's going to be 108 over 6x. So all I've done is transpose this equation for the value of y. So this here is going to give us the function L as a function of x. So let's rewrite this out. So that's going to be 9x plus, well, 8 is going to be 4 upon 3, so it's going to be 4 upon 3 times 108, and x is in the bottom line there as well. So we have L as a function of x such that it's going to equal, well, that's going to be 9x plus, now whenever you multiply these out and divide, you're going to get a value of 144 upon x. So don't take my word for it, multiply that out and check that that is the case. So this is equation number 3. So this is the equation we're interested in. This gives us the length of the fencing as a function, the length of the entire perimeter here as a function of x. So let's take this function here, L of x equals 9x plus 144 upon x, and we'll put it onto the next page and we'll work from there. So what we're interested in finding is the value of x that's going to minimize the length of fencing. So we're going to have to find the rate of change of L with respect to x. That is, we're going to have to differentiate this function here. So you can say that L of x is going to equal 9x Now we're going to put this in a form that makes it easier for differentiating. We don't want x in the bottom line, so that can be written as 144 x to the power of minus 1. So whenever we differentiate that, that's going to give us L derivative of x, which is going to equal, well, the 9x, that's, remember, it's the same as 9x to the power of 1, so that's like 9. Okay, now x to the power of 0 is just a value of 1, so that's just going to be a value of 9. And this one here is going to be minus 144 x to the, and it's going to be 1 less than that, so it's going to be minus 2. So we can see that L derivative of x, we'll write it as 9 minus 144 all upon x squared. So we want to find the value of x that's going to minimise this. So we're going to get a minimum point, or we're going to get a minimum whenever the L derivative of x is equal to 0. So what we're going to have is the 9 minus 144 upon x squared is equal to 0. So we can then rewrite that as 144 upon x squared equals 9. So therefore we can say that x squared is going to equal 144 divided by 9. So therefore we can say that our x is going to be equal to plus or minus the square root of 144 upon 9. And don't forget the plus and minus here, it's both values whenever you're taking a square root. So when we take the square root of that, we're going to get x is going to equal plus or minus the root of 16. So x is going to equal plus or minus 4. Now it's not going to be a value of minus 4 because we can't get a value of minus 4 meters of fencing. The length is only defined as a positive value. So the answer to this must be x must equal 4. So the value of 4 meters for x. So that means we'll get the value for x, which is 4 meters, and that's really all information we were looking for. Now we could work out the total area then, the total perimeter of fencing. We could take the 4 and we could put it back into this equation here. So let's just do that and we'll get an answer for this. So we could say that L of 4 is going to equal 9 times 4 plus 144 upon 4, which is going to give us a value of 72 meters. So this gives you the total length of the fencing whenever we've got x is equal to 4. So this is going to be the minimum amount of fencing that you can use in order to ensure that the area remains at 108 meters squared. So you can see that by using optimization, you can use differentiation, that's calculus, in order to solve practical problems. So thank you for listening. I'll get you on the next video. Goodbye.